Memory. Background. I have a very vivid memory of the first time that I thought about memory and wondered how it worked. As a teenager, I spent many nights and weekends babysitting two adorable little blonde-haired girls who lived around the corner. One winter evening, they decided to entertain me with Christmas carols they had learned at preschool. Before they made it through the first song, I was struck by an amazing difference. Both had difficulty remembering the correct words, but they made very different kinds of mistakes. Carolyn's rendition preserved the meaning of the text, but she had to adapt the words to fit the melody. Simone, who was 2 years older, remembered the phonetics of each line and adjusted her text accordingly. Although I don't recall a specific example, this really was a long time ago. I can imagine, "Oh Christmas tree, how lovely are thy branches," being converted to, oh Christmas tree, you have beautiful boughs and leaves," Carolyn, and oh Christmas tree, who lively art by ranches," Simone. Now that I have studied memory for many years, I have a better idea of why the two girls sang such different versions of the same songs. At the same time, I also know that I should question whether this event happened at all. Sella Olmstad. For many people, reading excerpts such as this one will remind them of their own past holidays. They are likely to remark that some festive events are easy to remember, whereas others are close to forgotten. In discussing these memories with old friends or relatives, it may become apparent that two individuals have dramatically different memories of the same event. In other situations, memories for these same occasions may be accessed unconsciously. Odors reminiscent of a freshly cooked holiday meal can induce a warm and pleasant feeling, but it may take a few moments to realize that these emotions arose because the smells were previously associated with specific celebrations. At the same time that thoughts of past events are surfacing and receding, individuals may be using their memory in other ways as they strum a guitar, carry on a conversation, or study for an exam. This chapter helps to explain how and why memory operates in so many different ways. Chapter plan. To say that this chapter provides a brief overview of memory is a gross understatement. Entire textbooks as well as some full-term college or university courses are devoted exclusively to this topic. A number of scientific journals only publish papers on memory research, e.g. Learning and Memory, Neurobiology of Learning and Memory, and even those that are not as limited in scope contain dozens of observational and experimental studies on memory. For obvious reasons, therefore, each section in this chapter provides only a synopsis of some aspect of memory research in humans or animals. The focus across the chapter is to understand these different components of memory within a comparative cognition framework. The chapter begins with a discussion of how memory relates to other cognitive processes. The same issue came up in the previous chapter, when it was noted that cognition must be understood in terms of sensory system function. Indeed, a recurring theme in this text is that cognitive processes constantly interact. In the case of memory, almost no other cognitive process functions in its absence. The fact that memory is critical for most cognitive functions is the basis for recent theories on the evolution of memory, which are described at the conclusion of the first section. This is followed by a description of how memory is processed over time through separate phases of encoding, consolidation, and storage. The next section describes the historical distinction between short and long-term memory. Over the last 2 decades, these terms have gradually been replaced with working and reference memory, reflecting the fact that both involve active mental processing rather than passive transmission of information. Finally, an examination of the cellular and synaptic mechanisms of memory suggests that general biological principles of this cognitive process have been conserved across evolution. Preliminary issues. Memory seems to be one of those terms that needs no definition. After all, most people would say that they know what memory is, even if they are not always sure how it works. But scientists must be very careful to define all of the terms that they use, even those, or particularly those, that are common in everyday language. In the simplest sense, memory is the stored representation of past experiences. A more precise definition from cognitive psychology is the mental processes of acquiring and retaining information for later retrieval. Learning versus memory. Note that the cognitive definition of memory includes both the acquisition and retention of information. In the past, these two processes were separated into subcategories of learning, acquisition, and memory, retention, but the two are so tightly connected that they were often discussed as one topic. Although it may be possible to acquire information without retaining it, i.e., learning without memory, it is difficult to imagine how one could retain information that was not acquired, i.e., memory without learning. Given this tight association, it is surprising that, historically, learning and memory were studied in different ways. Scientific investigations of learning typically employed lab animals, such as rats or pigeons, to understand how stimulus-response associations are formed. Behavioral psychologists, working with these models, assumed that the principles of learning were constant across animals, even when the type of information to be acquired varied dramatically, e.g., learning that a bell predicted food, as opposed to learning how to find your way home. Insight from these studies, therefore, would help to build general theories of learning and, by extension, memory. See Chapter 1 for details, including the intellectual and scientific developments that led to the demise of this perspective, the behavioral perspective. Few researchers today believe that all instances of learning can be explained by stimulus-response associations, although, as outlined in the next chapter, the study of associative processes continues to be a fruitful research endeavor. In contrast to the study of learning, most memory research during the first half of the 20th century, during the first half of the 1900s, tested the ability of human subjects to remember lists of words, often nonsense syllables. The technique was pioneered by the German psychologist Hermann Ebbinghaus, 1850 to 1909, using himself as an experimental subject. Ebbinghaus purposely employed typically meaningless sounds because he did not want his memory for these items to be influenced by prior experience. In other words, he wanted to study how information is acquired, not how it is modified by existing biases or tendencies. Ebbinghaus's results, as well as those of his many intellectual successors, were often interpreted within an associative framework. For example, two consecutive words in the list were more likely to be recalled together, presumably because subjects formed an association between them during list learning. With the rise of cognitive science in the 1960s, the theoretical framework for investigating memory shifted from an associative framework to an information processing model. Most contemporary researchers have adopted the cognitive definition of memory with the goal of understanding how information is represented and processed during acquisition, retention, and retrieval. Individual researchers may focus on one part of this equation, e.g., memory acquisition, but there is a growing recognition that learning and memory occur together and should be studied as one phenomenon. The current chapter adopts this approach, discussing all aspects of memory in a variety of subjects, ranging from insects to birds to primates to fish. Indeed, because the subject is so vast and the interest in it so intense, memory is one of the few areas of comparative cognition research that spans the entire animal kingdom. The common thread in this work is an attempt to understand how organisms use new information to interact with their environment. Like other cognitive processes, memory is measured, most commonly, with some behavioral output. These can range from the modification of simple reflexes to complex verbal responses. A caveat to this definition is that not all behavioral change reflects memory. For example, muscle fatigue or loss of sensitivity to sensory input could alter behavior, but neither would be described as memory. As always, researchers must be careful to eliminate these potential confounds when interpreting their data. Relationship of memory to other cognitive processes. Given that memory is measured as behavioral change due to past experience, it is difficult to think of any cognitive process that is independent of memory. Read the remaining chapter titles in this book and try to imagine whether any of these could function in the absence of memory. As an example, identifying living things as plants versus animals may seem like an innate ability, but what about dogs versus cats, let alone Dalmatians versus Irish setters? This ability to categorize items correctly, covered in Chapter 9, obviously requires some element of memory. The same is true of all other cognitive processes discussed in this book. Of course, this makes it difficult to dissociate memory from functions such as decision-making, Chapter 7, tool use, Chapter 8, or social learning, Chapter 12. The problem is not new. In the 19th century and the 1800s, language impairments that we now call aphasias were diagnosed as memory disorders or a failure to remember how to speak. Despite these challenges, we and other authors believe that memory can and should be examined as a separate cognitive process. The rationale for this decision is that experience-dependent modification of behavior does not provide a complete account of the cognitive processes discussed in later chapters. Memory may facilitate functions such as spatial navigation, Chapter 5, but it cannot explain the phenomenon entirely. For example, most students have no problem finding their way to a lecture hall on campus, but it is unlikely that they are doing so by memorizing the route from one building to the next. Otherwise, it would be impossible to get there from a different location. Like many animals, humans develop a spatial map of their surroundings that allows them to compute current position in relationship to global landmarks. Memory contributes to this process by using past experience to update spatial computations. In this way, it is parsimonious to consider memory as a necessary complement to other cognitive processes. According to contemporary authorities on the topic, one cannot understand cognition unless they understand memory. Ashcroft and Klein, 2010. Evolution of memory. It seems almost trivial to say that memory improves an organism's fitness, as the ability to retain information over long intervals has obvious advantages for survival and reproduction. In evolution, however, everything comes at a cost. Memory requires a lot of brain power, which uses resources that could be devoted to survival and reproduction. Moreover, the fact that behavior is modified by experience means that it starts out being less than perfect. All animals make mistakes, particularly in new situations, some of which are deadly, e.g., eating the wrong food or wandering into the wrong place. Why then would evolution favor a process of behavioral change that depends on experience? The answer lies in the ever-changing world around us. In a perfectly stable environment, memory would not be necessary. Organisms could respond to the stimuli around them, and those displaying the most adaptive responses would transmit these behaviors to their offspring. But no organism has ever lived under these conditions, so it is very likely that rudimentary memory emerged in the simplest forms of animal life millions of years ago. Indeed, this may be one thing that distinguishes plants from animals, although not everyone would agree. Vaz, 1999. If memory evolved through natural selection, memory abilities should vary across species that inhabit different environments. Although plausible, this hypothesis is difficult to test in cross-species comparisons of memory. For example, imagine the difficulty of designing an experiment to compare memory in worms and monkeys. Deciding what the animals should remember, let alone how to measure it, is complicated by dramatic differences in sensory and motor abilities, as well as more complex factors such as motivation. Even if it were possible to demonstrate that monkeys have longer-lasting memories than worms, they also have a much longer lifespan. 1-year memory retention in monkeys may not be better than a 4-hour memory in worms. An alternative approach is to examine whether the type of information that animals remember matches the ecological constraints of their environment, or, more accurately, the environment of their evolutionary ancestors. The evidence is compelling in humans who show better memory for stimuli associated with snakes or spiders than with guns or electrical outlets, even though the latter pose a much greater threat in modern society. Ecologically based memory is also evident in food caching animals, such as squirrels and some bird species, whose survival depends on remembering the location of hidden food. These animals display better and longer-lasting memories for spatial information than animals who do not cache food in their natural environment. Some researchers have even speculated that the memory retention curve, i.e., how long a memory lasts, should mimic the time course of survival-related events in the environment. Indirect evidence for this hypothesis is provided by male stomatopod crustaceans, Gonodactylus bradini, which mate with females and then leave them to tend to the fertilized brood. If the pair interacts during the subsequent 4 weeks, approximately the time of brood development, the male is less aggressive with his former mate than he is with other females. Thus, the male remembers the female during the time that she is caring for his genetic offspring. Theoretically, his memory might decline after the period of brood care, when it is no longer adaptive to keep a record of the information. Unfortunately, this was not tested. Finally, the evolution of memory may also be examined by comparing memory abilities in members of the same species that inhabit different environments. Huntingford and Wright, 1992, conducted this experiment by selectively breeding 2 populations of stickleback fish, Gasterosteus aculeatus, one from an environment with high predation risk and one from an environment with low predation risk. The first generation offspring of the 2 groups, reared in the lab, showed similar rates of foraging, finding food in one area of the fish tank. Differences emerged, however, when an aggressor was introduced to the environment. Memory for events that predicted the aggressor was better in the group from the high predation area. See Figure 3.1. In the parent populations, fish in the higher predation environment were more likely to survive and reproduce if they could modify their behavior, i.e., escape, based on experience, an ability that was passed to their offspring. In contrast, fish in the low predation environment were able to forage without interruption, so using valuable brain resources to remember when an aggressor may appear provided minimal evolutionary advantage. A similar phenomenon was demonstrated in fruit flies, Drosophila melanogaster, in that successive generations of selective breeding produced a population of quick-learning flies with long-lasting memories, 3 hours, which is a long time for a fly. As with the fish, it was the ability to remember, not a specific response to a stimulus, that was transmitted across generations, because descendants of flies with the best memories were also better at learning and remembering completely novel associations. Figure 3.1. Inheritance of memory in stickleback fish. Offspring of fish from environments of high or low predation were tested in an avoidance learning paradigm. Each day, fish were given access to 2 compartments containing food. When they entered their preferred compartment, defined as the compartment they entered most frequently during training, they were presented with a simulated predatory attack. Offspring of fish from a high predation environment were quicker to learn to avoid this environment than were offspring of fish from a low predation environment. Okay, so you can see it's a bar graph, a side-by-side bar graph. On the x-axis is day from 1 to 15, and on the y-axis is the number of fish entering the dark compartment from 0 to 8. And the 2 sets of bars are low-risk population and high-risk population. Okay, so starting from days, on the left, you had a lot of fish entering the dark compartment at the beginning, and then slowly the high-risk population just stops entering the dark compartment. Makes sense because they're predators, whereas the low-risk population, they do slowly, stop entering the dark compartment, but way more slowly, and they still enter it quite a bit later, whereas the high-risk population just doesn't enter that apartment at all, and that compartment at all anymore after about day 6 out of 15, where 1 or 2 will still enter in the low-risk population by about day 15. These examples bring up an important point about memory. It is not a stored representation of past events, but a cognitive process that allows organisms to adjust their behavior in an ever-changing world. Indeed, models of cognitive evolution argue that the transmission of fixed behavioral traits versus the ability to learn and remember is a function of the stability of an animal's environment. As we noted previously, the ability to modify behavior based on experience would facilitate many cognitive functions, so it is very likely that memory evolved in parallel with the processes that will be discussed in subsequent chapters.